Right, so from class, we said that here's our nucleus. And we have, let's just say our first energy level with an electron in it. And we have an outer, we're just gonna, all right, so this is our outer energy level. If we go from the higher energy level or the outer one to the inner energy level, if our electron goes from the higher to the lower energy level, is it going to emit a photon or absorb a photon? It's going to emit a photon, right? So therefore, we should be looking for a number that is going from n equals. So the first number that we see should be higher than the second one. So it should be going from n equals, let's say, 100 to n equals 50, not 50 to 100, right? So which ones can we eliminate right off the bat? Okay, B and C, because that's absorbing the photon. B and C, and any other one? E, right? Because those are going from a low to a high, which means that in order to do that, it has to absorb a photon of light. So now we're left with two choices. If you don't know which one it is, you have a 50-50 shot at guessing the right one, but we want to make sure that you know which one it is. Which one do y'all think it would be? Why A? What? So what was your reasoning for A?
I barely understand it.
So Alyssa says D. Anyone else have any other?
I think it's A, because I think it will emit the highest energy.
And why do you think it'll emit the higher energy photon?
Because it's a big emission.
So that is true. From A, in A, it goes from energy level 6 to energy level 1. That's a way bigger jump than from energy level 6 to energy level 3. That's true, but there's a better explanation as to why. So we have to look at the series that we learned about, and there's 3 series. Now I'm going to zoom in right here, and we can just neglect the question for now, and we'll go over what those series are. So we first have our Paschen series. Our Paschen, and this is important. You need to memorize these and all of its conditions for this exam and for your MCAT if you desire to take that one day. So Paschen series. This emits a photon in what region of the electromagnetic spectrum? Something that taught you in class for sure, because I know you're in our MOS class.
Is it like the N equals?
Not necessarily. Oh, yes. So that's not the. Okay. Sort of, but no. So it emits a photon in the infrared, so IR region, and its final N value is N equals 3. So for example, examples here. So EM region, and this is our final N. And the example would be like going from N equals 10 to N equals 3. That would be an example of a Paschen series transition where it goes from, it doesn't matter what this one is. It could be N equals 100, it could be N equals 1,000,000. But as long as the final N value is N equals 3, it's going to emit a photon in the infrared region of the electromagnetic spectrum. That's the Paschen. That's the Paschen series. And again, that EM stands for electromagnetic spectrum, the area of which the photon is released. So the next one is the Balmer series. The Balmer series releases a photon in which region of the electromagnetic spectrum? Close, but not quite.
I know.
Without looking at your
Well, no,
notes.
I gotta look at the theme.
Okay, so
The
what Well, let's see. You see let's see, we can make an acronym or something. You see a ball, a soccer ball or a basketball, and you see it because it has light coming off of it in which part of the electromagnetic spectrum. We can only see in one area. Visible light, right? So it's in the visible light area. So you see a basketball because you can see visible light, right? Let's just see if that helps y'all, okay? I know when Rich and I took this class, we had some really weird acronyms for things.
Some appropriate, some not so much.
So we're gonna stick with the appropriate ones that are YouTube friendly, because we're not trying to get demonetized. Anyways, does anybody know what the final N value for the Balmer series is? N equals 2.
The teacher doesn't teach.
Who's your teacher? Oh yeah, that's okay. I mean that's not okay, but like
What time is our mom?
8:30
Tuesday, Thursday, 8:30 to 9.
You won't know.
8 a.m.
a.m. You get an extra 30 minutes. All right, so basically an example of the Balmer series would be from n equals 7 to n equals 2, where the final energy level is the second energy level. And that's always going to emit a photon in the visible light region of the electromagnetic spectrum. And again, this n value does not need to be 7. It can be anything greater than 2. So it can be 3, it can be anything greater than 2. So again, for this one, it can be anything greater than 3. So from 4 to 3 and so on. You can't be 3 to 3 because that makes no sense, right? There's no transition there. And the last series is the Lyman series. And this one releases a photon in which region of the electromagnetic spectrum? The ultraviolet. There we go. So UV. So the ultraviolet, and the final N for this one is what? N equals 1. So example could be like N equals 2 to N equals 1. See how like the transition from 2 to 1, the transition from 2 to 1 is only a difference of 1 energy level, but it's still going to emit a photon in the UV region, whereas the difference from, let's say, 10 to 3 is 7 energy levels, but it's still going to emit a photon in the infrared region, which is lower in energy than the ultraviolet region. So it doesn't always necessarily depend on the amount of energy levels that it's jumping through. A lot of the times it depends on the final N value. The only times it matters, the amount of energy levels it goes through, is when you have the same N value, that same final energy level value. So let's say we have N equals 1, N equals 1 for both of these transitions as their final. So we know that it's a Lyman series, right? It's going to emit a photon in the ultraviolet region. But let's say for this one, we start at N equals 10, and this one starts at N equals 5. Because we know that it's going to be UV region because it's a Lyman series, and both of the final N values are 1. But because this one travels a total of 9 energy levels, the change in energy levels is 9 for the top one, and the change in energy levels is 4 for the bottom one. We can say that this one's going to emit a photon with even higher energy than this one because it's going through more energy transitions, or it's going from a even higher energy level to energy level 1, whereas this one's just going from 5, which is lower than 10, to 1. So this is the only time we look at the difference in the energy levels that it jumped. So up here, we were looking at, someone said that A is right because it goes through more energy levels, which we can only say that if the final N value is the same. But the better reason why A emits a higher energy photon is because the final N value is n equals 1, which means it's a Lyman series transition, which means it emits a photon in the ultraviolet region of the electromagnetic spectrum. And that's higher in energy than this one, which emits a photon in the infrared region, because this is a Paschen series. So does that make sense for everyone in class and on Zoom? And I know we took like 10 minutes on this question, but that was kind of a little lecture because this is something that you may have not gone over yet. But does that make sense for everyone on Zoom and in class? Yes.
Can you tell us some acronyms to remember? Like, is it, how are you,
How am I doing what?
like, remembering the series and the,
And honestly, I just kind of memorized it.
I
But
mean, you can always be creative and think of your own.
yeah, so like, I mean, for y'all, I just made this one up on the spot that you see a ball because it has emits visible light. So obviously it's emits a photon in the visible light region. And this is something you just gotta memorize, like the n equals 2 is the final one for Balmer series. But yeah, I think for this one, we have a really bad acronym for this one, so I'm not gonna say it for that one.
Or, you know what, I started with it, just remember the LUV, Lyman.
Oh, this guy got it. LUV, love. And then it emits a photon, the final n value is n equals 1 because you only have one true love, right? Oh, there we go. Okay. And then Passion, n equals 3. Y'all are on your own for that one. Passion is a horrible name. I don't know who would put their last name as Passion. It doesn't go with much. Anyways, is there any questions on that question number 6?
Just remember RIP, because it's backwards, so past gen infrared, but so it's RIP backwards.
The answer is A, right?
The answer is A, in fact, yes.
So
For six.
ball, soccer ball,
Someone on Zoom was about to say something. Go ahead.
I'm sorry. No, you can finish. Go ahead.
Oh, we already finished, so go ahead.
Oh, okay. I was just gonna say, so it only matters like the distance between them if both ends are the same, like if it's the same thing.
Yeah, both final n values, right?
Yeah, so like if A would have been N3, then it would have like mattered. Well, obviously the first N would have been different, but like you get what I'm saying, right?
Yeah. So if for A, it's instead of 1, this was 3. Well, that would be the exact same transition. Okay, so instead of, let's say that was 7. So if it was 7 to 3 and 6 to 3, then we would compare the distances in which they traveled. So which one do you think would have a higher energy in that case? That's fair, John.
Uh, I don't know.
The one with the bigger energy transition, or the one that transitions through more energy levels, which one do you think that would be? A or D after our little revision here? 7 to 3 or 6 to 3? I think it would be 7 to 3 because you're starting off at a higher energy level, which is n equals 7, and you got to jump 4 energy levels to get to n equals 3. Whereas this one, you start off at n equals 6, which is lower than 7. You only have to jump 3 energy levels to get to 3. And we know that it's still going to emit a photon in the infrared region, but one of them is going to be higher in energy than the other, and that would be A. Does that make sense?
Yeah, it does. Okay, thank you.
Yeah, of course. All right. Do you want me to make another one up like this, or how do you want me to just come up with one on the spot? Is that what we want to do? Sure, let's go ahead and do it. Yeah, okay. You got it, guys. No problem. So, let me make this a little bit bigger for you. Which transition emits a photon with the highest energy. And I'll give you like 3 problems here. So I'll give you 4. I'll do 2 and Mitch will make up 2. So this. So problem 1. Let me just- That's question 1. Y'all can go ahead and work on that one. And I'll do question 2. And so y'all just circle or let me know. Wait,
You just want
yeah, just one answer.
So
So
no, select all that apply.
it's a multiple choice question, A, B, C, or D. And
Not today at least, or maybe today. I don't know.
to, let someone in class. Like, read, you know, is that 11?
Which one?
Answer C, 10 to
yeah,
I think so, yeah, 10 or 11. So,
So I look at the spectrum theory, but we have a visible light cloud.
like the wood ones?
Yeah.
oh,
So it's anywhere, so visible light will be anywhere from like 400 to like.
Is that between the right one?
Exactly, like ultraviolet, because it's above violet, and then infrared, because it's below.
Okay.
all right. So those are your 2 questions. You solved those. If you let's do 1.5 more minutes, just because I know this is for some of y'all, and maybe for a lot of y'all actually, according to the gentleman in class. Y'all's professor doesn't teach, so I know this stuff, that little lecture that we gave you at the beginning might be brand new stuff. So I'll give you a 1.5 minutes. What's up?
Done. I thought it checker is.
Yeah, just do one,
Yeah, that'd be one.
just do 1, 2, or you're in.
Yeah, yes.
Go get on there,
This
sir.
one, okay.
I want one.
No, or, oh my God, it's,
Yes.
49. Oh, wait, no.
All right. Time is down. I mean, what are you about to do, Rich? You want to explain this one or?
Oh, yeah, and I can create my two problems.
Yeah, you can make it after. So go ahead and explain these 2, Rich, and
All right. So which transition emits a photon with the highest energy? So if it says highest energy, what are we looking for? What series is that most likely going to be?
The line is you.
Lyman, yeah, Lyman series. LY, I think that's how you say it. Lyman series. Let me choose. Lyman. That's what we're looking for. What's the end final for Lyman series? So what's the final end? Yeah, n equals 1. So because of that, right? I mean, automatically now we're just left with option B because the last end final is n equals 1. That's the only one that's there. But if you didn't recognize that right off the bat, we can go ahead and eliminate C, right? Because what is that doing? Is that absorbing or emitting? Why?
It's going to lower and it's going to higher speed.
Exactly. So all of these, right, they're emitting photons. They're going from higher energy levels to lower energy. And then we said we're looking for Lyman series, right? We're looking for n equals 1. And in that case, this is only one problem. So one answer, that's D. N equals 9 to n equals 1. The rest of these, even though, or even if you didn't see that right off the bat, this is like 8 energy transitions, and this is 5, and this is 4. But don't always go off that because you need to go off the series first, and then you can go ahead. So, yeah, that is that. So. Just get this. Yeah, n equals 7, that's the correct answer for that. All right, so now for the next one, same sort of concept. We're looking for n equals 1, but wait, there is no n equals 1. How do we do it then?
The second highest,
Yeah, so that's our what series?
the Balmer,
Yeah, the Palmer.
And that emits a photon in what region of the electromagnetic spectrum? Visible light, right?
Let's go right to DL for sure. Visible light. So right off the bat, we eliminate option D again, because that's doing what?
it's going to a lower to highest.
So what does that mean about
So
photon?
that means it's not emitting energy.
It's absorbing, yeah. So we're looking for n equals 3, or sorry, n equals 2 to be our final, right? So for that, we can eliminate option C. Now we're down to either A or D. How do we determine which one is which?
Greater distance of energy transfer.
Yeah, so it's like, yeah, so this one goes like 1 energy level, and this one's like 2 energy levels.
So Susanna asked you, Rich, how do you know which series to use?
So you gotta look at what the question asks you. So if it says highest energy, think back to your electromagnetic spectrum. You can pull one up online. So yeah, think about your electromagnetic spectrum. So it's like ultraviolet, then for lack of a better drawing, visible light is over here, and the infrared's over here. So if you want something with the highest energy, you probably want something in the ultraviolet region, because that has your shorter wavelengths. Shorter wavelengths, higher energy.
And the equation for that is the energy of a photon is equal to the Planck's constant times the speed of light divided by the wavelength. So like Rich was saying,
So the higher the energy, so your energy and your wavelength are inversely proportional. So as you increase the energy, you decrease the wavelength. And same thing over here, infrared will have longer wavelengths because it's a shorter energy. And visible light somewhere in between.
so he said we should, if we're looking for the highest energy one, we should look for the final n value where n equals 1. But in question 2, there was no problem, or yeah, there was no answer choice in which the final
Equals 1.
equaled 1.
So then we had to go to the next one up, which was n equals 2. So with that, we determined that that would be our highest energy transitions for the ones we were given. And then because we had 2 of them with that, we said which one had the greater energy jump. Like it's like jumping off 1 floor of a building or jumping off 2 floors of a building. Which one's gonna hurt? 2 floors, exactly.
Let's go test it out right now.
So option B
I want.
will be the correct answer.
Does that make sense, Susanna? And don't lie to us. If you need another explanation, say so. Don't lie. So if there was no n equals 2, you would use n equals 3. Exactly. Exactly. But because we're looking, we know that the next one up from ultraviolet is the visible light region. We would look for the n equals 2 as our final one for the next answer choices. And then, like you said, if there was no answer choice where n equals 2 is the final answer, or is the final energy level, then we would go to n equals 3. And if you look at the trend, like if you see a trend, the n equals 1, when the final n value is n equals 1, it emits a photon with the highest energy in the UV area. And when it's n equals 2, it does visible light. And when it's n equals 3, it is infrared. So we can kind of see a trend that if the final n value was n equals 4, we can estimate that maybe that would most likely be to the right of infrared area. So it would probably be in the microwave region or something. So it would be even lower in energy, just based on the trend from 1 to 2 to 3. So sometimes you may not be given a problem where it requires you to use the series. It may require you to use the trend, that as your final end value increases, it emits photons in lower energy areas of the electromagnetic spectrum, if that makes sense. We're using like such big words here and stuff, so I know it can get really confusing really fast.
But trust us, it's a lot easier than it sounds.
Do we have to memorize anything?
No.
No, just I guess the trend that I just said, that when as you keep going up, you realize that it gets further to the right of in the EM spectrum, so it's probably lower in energy.
All right, let's take it up a notch. So,
No, n can only be positive integer, because you can't have a -1 energy level.
you'll learn that later. It's something called the principal quantum number. So n is like the number of electron shells. Yeah. But we'll go into that at a later time in the semester. All right, let's take it up a notch. So last two things.
Oh,
All right, so which of the following would emit a photon with the, let's see, let's do longest. All right, your options will be n equals 3, n equals 1, n equals 4, 2, n equals 2, n equals 7, so n equals 3, and n equals 11 to n equals 3, and then for E, n equals 7 to n equals 2. All right, that's one. And then for the second problem, let's see, I'll just mix this up. Oh. Emits photon with the largest frequency.
It gave you, you wanted you to solve for the beats. It's like a bunch. Oh, what are you talking about?
Solve for the equal sign?
Like,
I large.
no, no, you had all of the all of the key information. I am bored.
All right, I'll give you all a bit of time to work on these.
which of the following were created? No, I don't have.
Right? Oh, we made. So let me know if you all can. Emit. I think that's how you spell that. All right, so. Which of the following emits a photon with the longest wavelength? That's question 3. And which of the following emits a photon with the largest frequency? Number 4. All right, give you all about, let's say, 5 minutes.
Was it read? high enough information for the reactor.
Let's do. Oh, wait.
The largest frequency that means smaller than I'm saying.
Where's your line?
But that device, you have to include your coefficient.
Oh, we got it.
For.
Okay.
Everything.
I make sure that every time possible on that review. I don't understand. Y'all get it. You know what? No students are getting that wrong. The family is a problem.
To be fair, Thursday.
How close to make this class and have a TA? He does have a TA actually.
Who?
He never there. Oh, never. You just said you taught that. Oh, you just taught the been too big.
Yeah, because, well, Dr. Armand was there.
We have to skip class. We actually
Oh,
had
he wasn't there. Yeah. Yeah.
Oh, and I think the Lord.
Wait, who is that?
How many, what did he get in? Like,
No.
Noah?
What is that? Start with you.
For everyone's TA.
Let's start with you, bro. Get it.
Well, at the beginning of the semester, they were in our class, and like, what would you do? You know, after.
Oh, he hasn't shown up since?
Yeah, it's usually session, but it's never like, never really understand what I teach it, but we're never not, we're. I'm gonna go to my parents. 8:30 a.m. I'm not going to call you. What the? Comes here at 8:30 a.m. People that. Oh, I've been to one house. All right, Rich, you think it's. Photon with the longest wavelength? That's a good one, that's a good one. Largest frequency.
This guy he switched up the wording. He switched up the wording. That's good.
I told you, pick it up a notch.
He kicks it up a notch. All right. I think everyone got an answer on that? Yeah,
All right, y'all have answers?
I think your Zoom chat is has increased, but.
let's see. That was from earlier, yeah. Sorry. You can, it was him who told me to do it. All right, looks like time is up.
All right. We're just following with emitter photon the longest wavelength. All right. So Zoom people, y'all can give me like, type something in the chat or in class people, raise your hand. How many of y'all looked at this question and were like, what the heck does this mean?
It's different than what the previous question said, right? But not really.
Anybody look at it and was like, how do I do this? Well, what the heck does this mean?
At first, yeah, before I thought.
Yeah, so at first, this is everybody's like initial thought. It's like, what the heck am I doing? So first thing I do is get the problem into terms I can understand. So which of the following can emit a photon with the longest wavelength? So let's put that in terms of energy. So y'all know how to do stuff like that. So longest wavelength. Does that mean lower energy or higher energy? Lower energy, yeah. So long wavelength, lower energy. So because of that, are we looking for something in the Lyman series, Balmer series, or Paschen series? Paschen. And what's our final N value? N equals 3. So right off the bat, we can eliminate options A, B, and E, because those don't have any N values, final N values, N equals 3. So now we look at our energy. This one goes 4 levels, and this one, it's kind of hard to see because it like goes on multiple lines, but this one's 8 levels. So which one would have a lower energy? Well, think about it. You're jumping off 8 floors of a building as opposed to 4 floors of a building. Yeah. So 8 floors of a building, it would hurt. So that means that it's more energy required. So, or it's more energy levels you jump down. So you can eliminate D, and our correct answer is option C. Because that's our lowest energy out of all of these options. So any questions about that, about how I got there? Zoom people, y'all chilling? Or cold as ice, all right. Which of the following emits the photon with the largest frequency? All right, let's get this into terms I can understand. So let's get it into terms of energy. I always put stuff in terms of energy because why? It's easier. So if something has a high frequency, what does that mean about its energy? Is it going to be high or low? High energy, right? So high frequency, it's high energy.
And what's the equation you use to prove that?
Energy equals Planck's constant times.
Exactly, Planck's constant times the frequency. All right. I'm gonna show you all a cool little trick. So you notice how in this equation, E equals hc over lambda, and then E equals hv. Notice how energy and frequency are on the numerator. That means they're directly proportional. So as one increases, the other increases. But for lambda, one's on the numerator, the other one's in the denominator. So as one increases, the other one decreases. I don't know, if you are math people, that sort of helps. But emits a photon with the largest frequency. So we've already stated that larger frequency means larger energy. So if it's a larger energy, which series are we going to be looking at?
And it was
Which is our
Lyman.
Lyman series, exactly. So we can go ahead and eliminate options E, C, and A. So now we're left with B or E. Now, which one between B and D has a higher energy? Yeah, barely. This one, you're jumping off 6 floors of a building. This one, you're jumping off 7 floors of a building. So 7 floors of a building, more energy levels. So option D, largest frequency. All right.
And boom.
Boom, boom, pow, Bob Jones. All right. Questions about that?
How are y'all feeling? Everyone give us a little response. How are y'all feeling about these things now? Or after the few problems that we have done?
Thumbs up.
Nice. We love to hear it. Was that John?
Yeah.
Nice. Good stuff, John. Thank you. Good job, Susanna. Thank you, everyone. All right. Let's see. Do you want more problems like this, or you want us to go on to a different topic now?
Let's go to the way you actually have to solve and all that.
Okay, so let's see. We had a problem highlighted somewhere, right? Let's do question 7.
Right, using Bohr's equation for the energy levels of the electron and the hydrogen atom, determine the energy in joules of an electron and the N equals 4 energy level. Okay, and you're going to do that by this equation right here. E equals negative RH times 1 over N squared, where N equals the energy level, and then your Rydberg constant is going to be equal to RH. And for this problem, it's 2.01 times 10 to the negative 18.
We're at 2.18 times 10 to the minus 18. Because
It probably
Yeah.
1.8.
so
You said this is called Bohr's equation.
Bohr, yeah, Bohr.
Bohr's B-O-H-R.
Not to be confused with Rydberg.
That's 2.18. Yeah.
That's an 8.
Let me give you a stencil, Rich. I actually bought one yesterday.
Nah, also this worksheet sucks because you can't rate like that. Can't write a link.
What do you mean for this problem? Is there multiple or does it tell you in
So, yeah, there are actually multiple Rydberg constants, because remember in class I talked about how in one Rydberg constant for the Bohr equation, it's 2.18 times 10 to the negative 7. But there's also this one for the Rydberg equation, that's 1.097 times 10 to the 7
you use 2.18 times 10 to the minus 18,
for this one. and
which
then-
involves energy, and the other constant you use when it's the 1 over wavelength.
Yeah, 1 over lambda equals RH times 1 over n final squared minus 1 over n initial squared. So use this one with that.
The equation says negative RH, so that means the RH is positive.
No.
The negative sign is like in the equation, so like you make it negative in the equation.
So it's not usually.
Yeah. Oh, I
I
might,
might, not put error in that.
yeah. So it's negative if you do n final minus n initial. If it's n initial minus n final, you would flip it. It's, yeah, you take the negative away. But I always do, Rich and I always do where the final, it's final minus initial, because that makes more sense, because usually like when you talk about displacement or change in something, it's always final minus initial. So if you use final minus initial, it should be dealt 1 over lambda. So RH is just the Rydberg constant. So that, like Rich said, is either, if you're using the 1 over lambda, it's 1.097 times 10 to the 7. Or if you're using the one with energy, which is the Bohr's equation on the right under answer choice D of question 6, energy equals negative RH 1 over n squared. Yeah.
So remember when you're given wavelength, use the one with 10 to the 7. And when you have a question like this with just energy levels, use the 2.18.
The equation, this is supposed to be a negative sign for the equation. I'm just trying to figure out how you could end up with negative energy. Unless it's the final minus initial.
The final is always smaller than the initial, remember?
Yeah, but it's only one n value.
Oh. Oh, I see what you're talking. Is it positive? No. Yeah, the negative RH is for this one. This one's positive. That's one.
Yeah, well,
Squaring anything is positive, so. This isn't like a physics thing, but the negative energy means like you release energy.
yeah.
Or could be that.
Give you about 1 and 2 more minutes. Oh, you want to zoom out, Rich, because they can only see. Like, sorry.
Oh, that's why it's negative. Summation.
Oh.
Yeah, this one's negative.
Okay. That's not, I was looking at the key. It is Satan. So question 7. See. And
This is question 6, not 7.
We're using number 7. Using the board equation.
What? I thought we were doing number 6.
We already did that. Yeah, so
Nah.
about 1 more minute for question 7, using the Bohr's equation.
Oh, we're doing number 6.
We already did that. Yes, we did. So we're like, okay, I already crossed the answer choices out. Then we circled, figured out it was A because that's alignment series. That's what I did all that. That's definitely that's the easy one we did. All right. I guess it's just fun.
Sorry, I got some stuck in the throat. All right. Using the Bohr equation for the energy levels of an electron in the hydrogen atom, determine the energy in joules of an electron in N=4 energy level. All right. We use this one. E equals negative RH times 1/n squared. So we plug in all our values. It is our energy equals negative 2.18 times 10 to the negative 18 times 1/16. And I got that 16 from 4 squared because 4 times 4 is 16. And if you plug all of that fanciness into your calculator, you'll get answer choice option C, negative 1.36 times 10 to the minus 19 joules. So yeah, it's just a matter of plugging into your equation and solving for the values. Can anybody tell me why we have a negative energy? But it's not emitting anything because it's only one energy level.
But what if it was n equals 3? It would be 1/3 squared, which is 9. Which is also 9. And if it was n equals 1, it would be 1/1 squared, which is also 9. I don't.
All right. Think about how an electron moves, right? Throughout an orbital. Like think about how it's moving. So if it's moving right, it would be what's it called? It's what's it called? What am I trying to say? System, or yeah, it's doing work on the what am I trying to say? So it's doing work onto the surroundings. So it's releasing its energy, making it negative. Because like for me, I just thought of like when an electron moving around, that probably generates some heat. If it generates some heat, there's probably exothermic. So yeah, that's why that's at least the logic I use to explain to myself of why that number is negative.
Jonathan said, where's the 1/16 come from?
So that 1/16, I just went ahead and jumped the gun here, but that's supposed to be 1/4 squared. And if you square the number 4, you get 16. So yeah.
You gotta stop using such a chunky marker, bro. What is that?
Sometimes you gotta add the chunky to remove it.
For sure.
There.
That's nice. All right. Let's see. All right. So it is 4 o'clock and we actually have a meeting to get to right now, unfortunately. But you can take a picture if you want of question 9, and it'll be the first thing we go over, and the next time we're gonna go over another worksheet that we made last semester, which was kind of identical to some of the homework problems that are on your take-home assignments for this week. So you can take a picture. Yeah, you know what? Go ahead and everyone, you can type in AP Chemistry Practice Test, Chapter 7, Atomic Structure and Periodicity into your internet browser of choice. And some thing's gonna come up as a PDF, and you can do all these problems again. There's even more questions, so then as you learn more about the stuff that we're teaching this for this next exam, you can go through the questions like, oh, I saw question 27, but I didn't know how to do it then, so I just learned how to do that now in class, so let me go try question 27 again.
When is your exam, by the way? Y'all know? It's always good to have that date in mind so you can study.
And we should start studying yesterday for the next exam, okay? Because there's so much stuff.
But even if you didn't study from yesterday, you can start studying today.
Exactly.
Study means the way we want to.
You grind out what you do know.
Thank you, Alex. That's always good. Saw that one video. Have y'all seen Rocky? He's like, come on, Rock, there's no tomorrow.
Okay. What did you say, Kennedy?